Today, we're going to peel back the skin on a modern aircraft and look at something you almost never see, but that is absolutely critical: the electrical system. It is, without a doubt, the unsung hero that makes every single flight possible. And we're going to dig into exactly how it all works. I mean, really think about that for a second. You see these giant engines, you see the massive wings, but what's running all the computers, the navigation displays, the lights inside and out? It's not just one simple thing, it's this incredibly sophisticated web of power generation and distribution. So, here's our flight plan for this little journey. First, we'll touch on why the system is so important. Then, we'll get into where the power actually comes from, how pilots control it, and finally, we'll talk about the golden rule of aviation safety that underpins the entire design. Right, let's dive in. Powering modern flight. I really do think of the electrical system as the unsung hero of the skies, because honestly, without it, a modern jet is just a really, really expensive glider. So what does it actually do? Well, at its core, the system has three main jobs. First, it has to create power out of thin air. Second, it has to tame that power, regulate it so it doesn't just fry all the sensitive electronics. And third, it has to send that power everywhere it's needed, especially to those absolutely critical flight instruments. So, how do you make electricity on a plane? It all comes down to a really basic law of physics: electromagnetic induction. In simple terms, if you spin a magnet inside a coil of wire, you get electrons moving. And that flow of electrons? That is electricity. It's the same idea that powers our entire grid, just happening in a super compact generator bolted to the aircraft's engine. And the number you'll see over and over again is 28 volts of direct current, or 28 VDC. That's kind of the industry standard. It's a sweet spot, enough power to run the aircraft's core systems, but not so much that it's overly heavy or dangerous to manage. Okay, so let's move on to the next piece of the puzzle. We know the principle behind making electricity, but where does this journey actually begin on the plane itself? What are the sources? Well, believe it or not, an aircraft has three main power sources. The heavy lifters are the generator and the alternator. They're both spun by the engines when they're running. The main difference is pretty simple. Generators make DC power right out of the box, while alternators make AC power that then gets converted into DC. And then you have the battery, absolutely essential for getting things started and serving as the ultimate backup. And let's spend a second on that battery. It's not there to power the whole flight, not even close. It's designed to be small, simple, and super reliable. Its main job is to provide that first jolt of electricity to get the systems and engines going on the ground. And after that, it's the ultimate safety net. As soon as the engines are running, the alternator or generator takes over and starts topping it off, getting it ready for the next time it's needed. Okay, so we're making power. Awesome. But a flood of raw, unregulated electricity is just as useless and dangerous as no electricity at all. This brings us to how we control that flow. Who are the gatekeepers of this system? Well, the pilot's main point of contact is this: the master switch. It's usually this split rocker switch with two distinct halves. So, step one, the pilot flips the right side, which connects the battery and brings the plane's basic electronics to life. Then, once the engine is started, they flip the second half. That brings the alternator online. The main power system takes over, and it starts recharging that battery. Now, deeper inside the system, you need protection from power surges, and that's where fuses and circuit breakers come in. They do the exact same job. They're like a safety valve. If too much electricity tries to rush down a wire, they pop and cut the connection. The only real difference is the tech. Fuses are old school, they literally burn out, and you have to replace them. Circuit breakers are the modern upgrade. They just trip, and you can push a button to reset that. But it's not all manual switches and breakers. The system is also full of smart switches that do things automatically, giving you a layer of automation and protection without the pilot ever having to think about it. And this is where we find two components that people often mix up: solenoids and relays. A solenoid takes electricity and turns it into physical, linear motion. It pushes or pulls a rod. The starter in your car is a perfect example. A relay, though, is a remote-controlled switch. A tiny little electrical signal tells it to flip a much bigger switch that controls a really powerful circuit. It's kind of like using a tiny remote to turn on the lights in a whole stadium. And of course, the foundation of all this is the good old-fashioned switch. Whether it's that big master switch in the cockpit or some tiny automated one buried deep in a computer, its job is always the same: open or close a circuit, basically to tell the flow of electrons go or stop. So we've made the power, we've controlled it. Now for the fun part. Where does all this electrical energy actually end up? What's the final destination? The short answer, pretty much everywhere. The engine starter is a huge power hog. It needs a massive jolt to get that big engine spinning. But then you have a constant draw from what's called the glass cockpit, all those beautiful digital screens that feed pilots information. And of course, you've got all the lights, the radios, and dozens of other flight instruments that are basically the eyes and ears of the aircraft. And that brings us to our final, and honestly, the most important section of all. This entire complex system is built around one single golden rule of aviation design: redundancy. It's all about safety through duplication. Here's a perfect example: the magneto system. A magneto is basically a little self-contained generator whose only job is to create the spark for the spark plugs. Now, even a small aircraft engine doesn't just have one of these, it has two. They're completely independent of each other and the plane's main electrical system. The logic is simple. If one fails, the other one just keeps the engine running, no problem. And this takes us right back to the battery. In a worst-case scenario, both the primary generator and the alternator fail. The regulations are crystal clear. That backup battery has to be able to power the essential flight instruments for a bare minimum of 30 minutes. That's the final safety net. It gives the crew a half-hour window to get the plane on the ground safely. This all comes back to a classic engineering philosophy you'll hear all the time in aviation, in spaceflight, you name it. 2 is 1 and 1 is none. What it means is, if you only have one of something important, you really have nothing. Because the moment it fails, you're done. Real safety, real reliability begins when you have a backup. So, the next time you're on a flight, just take a second to appreciate that complex, redundant, totally invisible web of wires and circuits that are humming along, keeping everything running perfectly. And it kind of makes you wonder, right? What other invisible systems, built on this exact same idea of redundancy, are out there keeping us safe in our everyday lives?